Hey everybody, today we're going to do an algebraic example of the first derivative test looking at the function f of x equals x to the fourth minus 8x to the third. As we classify all the critical values as local maxima and minima, we will determine where this function is increasing and where it's decreasing. Let's go. So the first thing we need to do is to get a derivative of this. We're thinking about increasing, decreasing, local max, local min, all in terms of the signs of the first derivative. So here, f prime of x is 4x to the third, 4x to the third, minus 3 times 8 is 24, x squared. So critical values here are going to be places where the derivative either is 0 or where it does not exist. Now this is a polynomial, so it's never going to not exist. All we have to worry about is where this is equal to 0. So let's set f prime equal to 0. When I set a polynomial equal to 0, the main technique I'm thinking in terms of is factoring. Here, I have a greatest common factor that I can take out. Between 4 and 24, I see a greatest common factor of 4. And between x cubed and x squared, I see a greatest common factor of x squared. So let's pull all that out. When I do that, I'm left with x minus 6. Now, if this product on the right-hand side is equal to 0, then one of the two pieces has to be equal to 0. So either 4x squared is equal to 0, in other words, x is 0, or x minus 6 has to be 0. In other words, x equals 6. So these are going to be the critical values. Now we need to classify each of those as a local maximum, a local minimum, or neither one. The way we're going to do it again is with the first derivative test. We're going to figure out where the derivative is positive, where it's negative, and use that to classify these critical values. Let's make a sign chart. So I'm going to label x values that correspond to these critical values. And I'm interested in the sign of f prime. So let's write that here. Now, f prime as a polynomial is a continuous function. So the only way it can change from positive to negative is if it's 0. I've labeled both the places where that can happen. So all I need to do to determine where the derivative is positive and where it's negative is to check a single point on each interval. If the derivative is positive at a single point in this interval, it's going to be positive in the whole interval. If it's negative at a single point in that interval, it's going to be negative over the whole interval. Let's pick some friendly values. For x less than 0, the easiest number I can think of is x equals negative 1. Let's test x equals negative 1. Okay, what do I mean by test x equals negative 1? I mean plug it into the derivative to see whether the derivative is positive or negative. Now, I could plug it into either one of these, do a little calculation, get a number out, and figure out whether it's positive or negative. I want to be a tiny bit lazy here, lazy in the best way possible. I'm going to use this form of f prime, and I'm not going to worry about what exactly the value of the derivative is. I'm only going to worry about whether the derivative is positive or negative. When I plug in x equals negative 1, 4x squared is going to be positive. Negative 1 squared is positive 1. And when I plug in negative 1 here, I get negative 1 minus 6. So also negative. A positive times a negative is a negative. The derivative is negative. At that point, x equals negative 1, and therefore, on the whole interval, negative infinity to 0. Next, between 0 and 6. Let's take another convenient point. Let's test at x equals positive 1. Again, let's use the factored form. When I plug in x equals 1, I get a positive, again, times a negative. 1 minus 6 is negative. Positive times a negative is negative. So f prime is negative at x equals 1, and therefore over this entire interval. Finally, x greater than 6. Let's test x equal 7. I plug in 7 here. I get a positive times positive. 7 minus 6 is going to be positive. Positive times a positive is a positive. Therefore, the first derivative is positive for x greater than 6. Okay. I remember that when f prime is negative, the function itself is going to be decreasing, and when f prime is positive, the function is going to be increasing. When I've got my sign chart done, it helps me to draw lines reflecting that fact on top. So I go like this. And I immediately from this can observe that I'm going to have a local minimum at x equals 6. X equals 0 is a critical value, but it's neither a minimum nor a maximum. Finally, we can see that this function is going to be decreasing from negative infinity to 0 and from 0 to 6, and then increasing from 6 to infinity. Let's write that in interval notation to complete this problem. So we have this function is increasing from 6 to infinity. Notice I'm using open intervals. I don't want to talk about whether the function's increasing or decreasing at 6 because I already know the derivative is 0 there. It's a critical value. It doesn't make sense to talk about the function increasing or decreasing at that single point. The function is going to be decreasing wherever the derivative is negative. I know the derivative is negative from negative infinity to 0 and 0 to 6. Let's write that in interval notation with a union symbol. Negative infinity, comma 0, union 0, comma 6. So there's one question here at the end of this problem that we should respond to very quickly. Why can't I just write negative infinity to 6? Isn't the function actually decreasing on that entire interval? Why did I leave out 0? Well, it is a fact. If you draw the graph, you will see this function is actually decreasing from negative infinity to 6. However, the way that we are checking for increasing and decreasing right now is by using the first derivative. We know that the function is going to be decreasing when the first derivative is negative. Here, we aren't prepared to say that the function is decreasing on that entire interval because the derivative is not negative on that entire interval. In order to determine that this function is really decreasing on the entire interval, negative infinity to 6, we need to bring in information from outside of our first derivative analysis. We're not doing that here, so we want to be conservative in our conclusion and stop.